So we left off last video telling this important point that the derivative of the displacement is the strain. So we find the strain from here. We see that it's constant here and constant here. So as we are integrating more and more and more, we're going farther and farther out. The position is getting more and more longer. It's longer and longer. And this can be understood by two ways. The position adds up. So if we have a point here, it moves there because of the piezoelectric strain. It also, by default, it moves this point over, and then this point also wants to move even more because of the piezoelectricity. So there's two things adding up. There's one, the initial change of the little atom or little sliver of material before it moving, and then itself wants to grow and expand due to piezoelectricity, or due to that strain which is occurring uniformly in the material. So this is the strain which builds up in a material. Next, we want to talk about resonance displacement. And before we may actually, and then we're actually going to realize why I'm going over all of this stuff. We had this mass spring damper system. Why didn't we just use it directly to model piezoelectricity? We already found the spring constant. What was the spring constant? It was 1/2, I think, A L over S. It was like the NX delta D squared, or now we have this term U squared. So we had this spring constant before. I think this was actually underneath here. That was because if you are making the spring longer, it's actually easier to stretch it longer because you don't have to induce as much strain. So I think it's this is on the bottom. Anyway, so the point was that, hey, why don't we just model this, and obviously the simplest models are sometimes the most revealing and you can understand a lot of stuff from it, but actually it ends up being wrong. You can't model the spring constant like this for higher frequencies, and the reason is because this spring model, or this equivalent stiffness that I mentioned, A L over S, A L S, this is for a uniform strain. But an uniform strain was if you want to look at the displacement and the position X, uniform strain would just lead to constant slope of the displacement. But actually in resonance, or you can say when we apply an electric field with a frequency, not necessarily at resonance, but whenever we have a frequency applied which is somewhat high, we have to consider a different model. And this is because originally we had this uniform strain case, just like I mentioned. We had this uniform strain, but we actually don't get this happening. We actually get this happening. But this is a DC. And this is the actual displacement profile in the AC case, where we have a larger, and this is again the position and the displacement. So this actually, it doesn't end up being a straight line when you apply a electric field, which is to its resonance point. And the reason we can kind of understand this is that if we look at this material, it's going to kind of be hard to imagine without maybe a simulation. But when when this thing is vibrating back and forth, this piezoelectric plate, so you can kind of see that this part right here, let's divide into 3 parts. These parts are really pulling out. They're really tugging at this middle part. This middle, due to their inertia, the inertia mass times acceleration, or in this case we have mass u double dot. This is kind of a force which is happening, and these are really tugging at it, tugging at the middle portion. So we can understand that the middle portion will have higher strain. So what does the strain look like here? Let's just draw it here. And remember, the uniform strain case was just a straight line. But in this case, we will have this. And these are sinusoidal. These have a sine format, something like this, pi x over l. So this is the basic outline, or and this can be calculated, and we're actually going to do it somewhat. So basically, this is also in a sine form, although I didn't do the best job drawing it. But basically, we have zero strain at the edges. We have the most strain in the center, and this is for, again, the AC, and this is for the DC case. And see, because we kind of have these more tugging at the edges, we have more stress in the middle. This is more stressed out because these are pulling on it than the edges. So because the middle portion is more stressed, or strain is equal to, wherever you have stress, you have strain. So X equals SX. So wherever you have the stress, you have strain, you have a direct relationship. One is higher, so we have a higher stress, we're going to have a higher strain. So we have high strain in the middle because these have a lot of force putting on them due to the vibration of the outside portion. And then look, this goes to zero. This is another portion. Now we understand why we'll probably have maximum stress or maximum strain. We're drawing strain in this curve, the curvy X. We're drawing strain, and this is the regular X. This is the position. But why do we have minimum or zero? Actually, the thing is actually zero at the edges. At the edges we have zero, and the reason we can kind of understand this is because at the edges, we kind of model. If we look at the edge, we have we have these spring type of things, and this kind of goes on, right? But there are no forces, or there's no inertia. This mass times acceleration, there's nothing there. And this mass times acceleration is actually what causes the main resultant of the forces and this vibrating structure. So because there's nothing on this side to tug at it, there's actually no stress at the boundary. So this is one of the boundary conditions. So we have at plus or minus L over 2, assuming the 0 points in the middle, the stress equals 0, which also means the strain equals 0, because there's nothing able to pull on it. Because to pull on something, you need to have something on the other side, or you're just moving and you're not getting pulled on. So therefore, there is, if you look at this kind of little portion, let's call it a differential portion, X, we have something on this side pulling on it, but on this side we don't have any thing pulling on it or pushing on it due to the inertial forces. So therefore, we kind of understand that there's no stress on the edges, and this is sinusoidal. A little better figure of this can be demonstrated on a bigger graph. And I'm drawing these, in the same kind of scale. Although at resonance, we know that there's a lot more vibration which has happening. So we know there's a ton more strain in the middle. They're not comparable. I'm just drawing in the same plot. So this is the AC and DC, and this is the strain. So this is something you absolutely must know. That this is how the strain reacts. And there's no strain or stress on the outside. But see, if you want to look at the displacement, we're going to draw in a different color, green. If you want to look at the displacement for the AC case, and I'll just highlight the AC case again in green, so we can kind of remember. We still, when we're going to the edge, we're still going to integrate, right? We're still going to integrate. So this is why when you integrate this cosine function, you kind of get this. Because over here, there's not really much being added. And it's not much extra value, so therefore the displacement doesn't change so much. So this is basically this integral which starts out small, even though the rate is big, but you gotta go some distance, and then you end up with doing this integration over here. You end up doing integration here to get this displacement which is occurring. So I believe this wraps up this topic of why we can't use the spring constant, because the spring constant is relative to this constant displacement. Constant strain. But in reality, we have this kind of weird looking strain here. Like, not weird looking, it's a sinusoidal, but the sinusoidal strain is going to need some modifications. So we're going to see there's going to be something like an 8 pi squared modification to this spring constant, which was ALS. And we could easily understand the spring constant and the relationship. You could derive it by thinking, okay, if I make this bar bigger, if I make the area bigger, then I will have to apply more force to it to get it to move the same distance. Let's just draw the little bar. If I increase this area over here, then it'll be bigger, so it'll be like more stiff, like pulling a really stiff bar, or a really like pulling on a thin wire, or a really long fat kind of pole. It's just going to be a lot stiffer, the fat pole. And then so that's why the A is on the top. As you increase the area, you increase the stiffness. The second is this L. And as you increase the length, you may kind of intuitively think that it's going to be more difficult to pull. But think about this. Think about you have a really long rubber band, and you're pulling on it. A really short rubber band. So basically, you can pull on the long rubber band with a small force. And basically, we know that the strain is equal to the stress times the here. But basically, if you have, this is actually, if you multiply this by the length, so the strain is delta L over L. Basically, what I'm trying to say is that if you increase the length, things get easier to pull in a longer distance. And then here, the elastic stiffness, which is actually the elastic compliance. So we increase the compliance, we're decreasing the stiffness. It's kind of opposite to a normal convention, where we usually, in mechanical engineering, we're usually used to using this Young's modulus, which relate the strain to the stress. But in piezoelectricity, we're often applying some type of stress or an electric field which causes the stress, and then which causes the strain. So therefore, it's more important to consider this parameter S, elastic compliance. So right, if you keep the area the same, then always this relationship is always true. So because this relationship is true, we generate more distress. Let's try this again. The way you think of why long things make a stiff spring. So let's take two pieces of material, or long things make, and this way, and we're both applying, and we're assuming they have both area. We're both applying forces this way, capital X, and this is actually just one spring, and this is actually two springs. So two springs put back together are more soft than one spring. And this is kind of like an intuitive reason why we get a L on the bottom, because as you increase this, the stiffness decreases, and you'll get more displacement for a given force. Thanks for watching.